Chemical reactions involve breaking and forming bonds. Breaking bonds require energy input, and forming bonds release energy. This is the big deal. This is the whole thing right here. Okay, so we can say that bonds hold potential energy. And we can measure that. We know how much. And this is a known amount. That's important. The energy that's given off in making the double bond OO is, this means change in energy. This means change. That's a delta. It's a little capital D in Greek. And we can call this is called enthalpy. H is known as enthalpy. It's heat energy. Okay. The opposite process, breaking those, requires the input. Oh, that reminds me, I'm sorry. A negative sign means heat given off, heat emitted. And the positive sign means heat absorbed. You're looking at your system, your molecule, and so he's gained that much heat. And the negative means your molecule or your atoms, your system in its entirety has given off that much heat. It's just a convenience or an accepted way of doing it. But notice that it's the same amount of energy. It is very much predictable. Okay, and this is kilojoule. So 1,000 joules, and this is per mole of the O2. Or it's actually as written, I'm sorry. It is as the equation is written. So it could be either per 1 mole of O2 or we better leave it like that because it could be per 2 mole of the O atoms. It depends on how many are in the thermochemical equation. And we're going to talk about that in a little bit. Not important right now. But in order to break, this is CO2. I'm just supposing. Ultraviolet UV radiation comes in and you will break that bond. That takes a lot of energy. That is the bond energy. The bond energy is the amount of energy required to break a bond. How about that? That must be absorbed to break a chemical bond. Let's look at an overall scenario during a chemical reaction. So in a chemical reaction, the bonds of the reactants must be broken, and that takes energy. So we're going to make that a positive amount in. And, oh, there she is. Oh, rats. Okay, I didn't have to write it. Okay, bond energies. Here's a sampling. This is from your textbook, and the way you read it is, this is a single bond between HH. This is a single bond between CH. And down here, let's do this one. This would be a single bond between hydrogen and sulfur. So we'd write this guy as C as SH. H. It's the energy to break that single bond. Down here we have our multiple bonds, and it makes sense that they would be larger than the single bonds. This one's kind of strange. Not strange, but this tells you, this is noteworthy, that N2 is very inert because it takes so much stinking energy, almost 1,000 kilojoules, to break a mole of this stuff in two. This reaction would be N plus N, breaking into its atoms. And that would take 946 kilojoules. Yikers. Here's another one. This is why CO2 is so inert. And this is carbon monoxide. I'm sure that's one of the reasons why he is quite dangerous as a chemical. All right, so let's do something simple. Let's just create water. This is the reaction that I'm looking for, is 2H2 plus O2. Remember, I don't write the 1 usually, to make water. Excellent. All right, now notice I'm going to start at a 0 point, and this way is energy increasing. Energy increasing, or yeah. Better way to put it is adding energy. Okay. All right. So I start off with my reactants, and first I'm going to add about 1,000 kilojoules, and then I'm going to add 500, and when the reactants form, I'm going to get out almost 2,000 kilojoules. So this is energy in, and energy out. Notice the arrows. Directions. Okay. The difference is the net energy change. That's how much overall, the products minus the reactants, how much energy is left over. So to break 2 moles of HH atoms, or bonds, I'm sorry, requires 872 kilojoules. So here's 2 moles of this single bonded guy. Okay. Now we need to break 1 mole of O double bond O. See, there's a 1 there, and it's O, O. Why moles? Because that's realistically what we're going to be working with in the laboratory, and working on the atomic scale does it no good. But again, I repeat to you, anything we can say about the molecules, we can say about moles of the molecules. It's just multiplying everybody by this constant 6.022 times 10 to the 23rd, this Avogadro's number, this collection. Okay, so now we've broken them. We have up here 2 moles of those guys and a mole of those guys, and we're going to form H2O. So here's breaking, here's forming, and we get out of this guy almost 2,000 kilojoules out. And what do we have? We end up with 2 moles of H2O, and she looks like this. So we got 2 of those. And the net change is, notice the negative sign, about 500 kilojoules, and this is energy emitted, energy given off. And if you do this in the on the desktop, or I'll do if you see this reaction being formed, this is a big old bang because it comes off very fast. The energy given off comes off very fast. Great. Okay. I'm not sure. A change in the heat energy. Well, let's start up here. The most common energy generating chemical reaction is combustion, reaction of fuel with oxygen. We've talked about that before. The reaction is what we say is exothermic. Exo like outer, and thermic meaning heat. This is outer, out, and this is heat. So exothermic means releases heat. The amount of which depends upon the amount of fuel. That should make sense. If I have a small pile of coal versus a ton of coal, I'm going to get a different amount of heat out. It's written delta H, change in enthalpy. The heat of combustion, sometimes you see a little baby C down here to tell you it's the heat of combustion. And combustion, remember, means burning in oxygen. So we've talked about the burning of methane before, and now we can figure out how much we can get from one side to the other and how much heat would come out. And this really is what Columbia Gas will do. They'll figure out how much heat they're going to need to heat the houses in Columbus and do this calculation, because this overall reaction can be determined how much heat is coming off of this. All right, here I'm going to have to break 4 CH bonds. Here I'm going to need to break 2 OO bonds. What's my reward? I get, I form 2, this is kind of strange, but you form 2 C double bond O's. One here and one here. We got to be sure we add them up. We do good bookkeeping here. And then over here, we form 4 OH bonds. There's 1, there's 2, there's 3, there's 4. So we get energy from each of those formations. And we go to that table that we looked at, and if we did it, we would find that overall, the delta H for this reaction is equal to negative 814 kilojoules. Exothermic, heat given off, and quite a lot. That's pretty large, which is why methane is such a wonderful thing to use to heat our homes. Let me show you the details of this in another example. How about the combustion of ethanol when you drink alcohol? There's the reaction. Again, it's combustion. See? Remember, this guy's called a hydrocarbon. He's with oxygen. He's carbon, hydrogen, and oxygen. And a complete combustion of a hydrocarbon is always going to make these two products. Okay. We balance this, not very well. I'm going to have to write these myself. Okay. It goes 3 here, 2 here, 3 here. Let's just ignore these guys. And this is a 2 here. Okie dokie. Take you out. So, first step? We draw the Lewis structures. Why? So that we can see who's bound to who and count the number of bonds. So the number of CH bonds, you can tell now explicitly, is 1, 2, 3, 4, 5. I put a table. And I write the different bonds broken. The enthalpies, this is from your table. This is from the Lewis structure. You can tell that. And then this is the coefficient, and then this is the number of bonds. Alrighty, so if we look for CH, we can see that it's 5. CC, right here, it's 1. CO, 1. OH, 1, and 3 of those guys. On the other side, we have 1 and 2 here, but notice I've got 2 of the molecules. So that is 2 times 2 equals 4 of those bonds. And same thing with here, we've got 1 and 2, but it's 3 of those species, so I've got 6 bonds. And again, these are from the table. You don't play around with the signs yet. You figure out the total, and this one you can realize is going to be energy given off. This one is positive. This one's is energy absorbed to break the bonds. This is called a summation sign. As is this. It's a sigma, capital sigma in Greek. And we take the total of the bonding energies. Okay, of the reactants minus those of the products. This comes out to be 1281 kilojoules, very exothermic. And so you watch your signs. The negative means that it's exothermic. And you might ask, what makes a huge explosive like nitroglycerin? Nitroglycerin is an oily yellow liquid, and it used to be very dangerous. They would use it in mining to blow things up, right? But if you shook it, it could explode. And that's because it makes very stable gases with very large bond energies. So the reactants are very unstable. The reactants here, very unstable, small bond energies. And the products are very stable. So we've got a big change in energy. We have bond energies. We can write out the equation. Bond energy of the reactants minus the sum of the bond energies of the products. And boy, it can get complicated for these. We aren't going to do anything as complicated. What I would like you to be able to do is do this kind of calculation for perhaps the formation of water, or looking at the problems in the textbook, the formation of ammonia. For example, if we had N2 plus H2 making NH3. This is called the Haber process, and it balances like this. So that I would like you to be able to determine delta H for the reaction. And this would be same deal though. Sum of the bond energy of the reactants minus those of the products. This is H2. Okay, and there's lots of numbers there, but here's the big payoff. It is really exothermic. It's almost 6,000 kilojoules per mole, and it really comes off fast, so it's a really big boom.